For this lesson, we are going to learn about waves. So there's different types of waves. Some waves need a medium to move through. And when I say medium, I mean like a material, whether it's air, water, or land. And some waves don't need a medium. Those are called electromagnetic waves. We will not be talking about electromagnetic waves in this lesson, but we will in future lessons. When we talk about waves, we want to talk about forces and vibrations. So waves are wiggles in space and time. They're caused by forces, so a disruption. So if you drop a stone in the water, right, what you did is you created a force in the water, and that water caused a disturbance that creates a wave that moves outward through the water that carries the energy. So waves carry energy from point A to point B. That's what waves do. So when we talk about waves, we need to learn some terminology. So a vibration is a repetitive back and forth motion, and more specifically, a periodic motion is something that repeats itself over and over again. So we can see here, some periodic motion on the left. The girl on the swing, she's swinging back and forth. The period is the same. That means it's repetitive over and over and over again. Like a clock is also an example of periodic motion. The clock goes around in a circle. The second hand goes around every 60 seconds. The minute hand goes around every hour. And the hour hand goes around every 12 hours. So that would be what we call the period of its motion. The frequency we're going to learn is how fast it goes around, or cycles per second. So periodic motion is one that repeats itself, and then on the right, either a lie detector or a seismic detector, one or the other, you can see that it's a vibration that goes back and forth and back and forth. So a disturbance from equilibrium. Equilibrium would be like the girl on the swing. That would be when she's just sitting at a vertical. That's your equilibrium position. So then she puts in energy to give her a displacement from equilibrium. And then the swing is restored by gravity. That would be the restoring force in that case that causes it to go back to its equilibrium position. So as she goes back and forth, gravity continually pulls her back. On the right, in the seismic reading, there's probably a spring there or just some tension in that metal rider that causes it to go back to its original position. Here's an example of graphing periodic motion on a sine wave. You can see the motion repeats itself over and over and over again. The spring in this case is your restoring force. So this is going to go up and down, over and over and over again. This is simple harmonic motion. Simple harmonic motion always creates a sine wave when it's graphed because it creates the same pattern over and over again. You can see one cycle goes from crest to crest, or you can measure it from trough to trough, but a cycle is where the wave repeats itself. We call this a wavelength, so the wavelength is the distance between two of the same points on the wave. Here are our terms looked at again. We got amplitude defined as the maximum extent of displacement from equilibrium. So when the pink ball is at the top or the crest or at the bottom, the trough, that is the distance from equilibrium. That's your amplitude. Cycle is one complete vibration. So if you look up at the top and you start at the top and you go the whole circle around, that's one complete cycle. You can see the ball on the graph goes from crest to crest. That's a cycle. The period is the time it takes to complete one one cycle. So like on an hour hand of a clock, the period is how long it takes to get around, which would be 60 minutes. The second hand has a period of 60 seconds, and the hour hand has a period of 12 hours. That's the time it takes to complete one cycle. And the frequency is the number of cycles per second. So the frequency of the hour hand of the clock would be 1 over an hour, or 1 over 3,600 seconds. The frequency of the second hand of the clock is 1 over 60 seconds, and that's measured in hertz. So cycles per second, that's known as a hertz. The relationship between period and frequency is an inverse relationship. So when the period goes up, the frequency goes down, and vice versa. When the frequency goes up, the period goes down. So the higher the frequency, the shorter the time between cycles is. There are two types of main two main types of waves. We have mechanical waves and electromechanical waves. Or excuse me, we have mechanical waves and electromagnetic waves. So mechanical waves require a medium for propagation, and waves move through the medium, but the medium stays in place. So a medium is the substance. So like water is a medium, air is a medium, the desk that you're sitting at may be a medium, any solid is a medium, any liquid, any gas. Those are all mediums. So as the wave moves through the medium, it doesn't actually move the medium. It moves through the medium. So if you think about a rope, the two people are holding the ends of the rope doesn't actually move. It stays in the same spot. So if you and your friend are doing jump rope and you're 6 feet apart and you're swinging the rope around, or if you just create whips in the rope, make waves in the rope doesn't move. You're still 6 feet apart. What happens is the wave moves through the rope. So that's one concept that's kind of hard to understand, is that the actual medium doesn't move. The wave moves through the medium. And if you think about the ocean doesn't actually move. Now the tides come in and out, that's a little different, but the ocean stays in the same spot. The wave moves through the ocean. There are three types of mechanical waves. The first one is a longitudinal wave. In a longitudinal wave, the vibration direction is parallel. So you can see in the picture below, the hand is moving parallel or in the same direction as the spring, and you can see the wave move through the spring. Where you have those condensed spring coils, that would be your amplitude. The wavelength would be the distance between those two compressed spring coils. So remember, your wavelength is your cycle. You can see as you compress it, the medium moves closer together, and then when you pull your hand back, the medium expands, and this creates these zones of high and low pressure. Sound waves are an example of a longitudinal wave. A second type of wave is a transverse wave, and transverse waves move perpendicular to the direction of motion. So here as the hand moves up, you can see it creates a crest, and then the hand moves back down, and it moves up again, it creates another crest. Those two waves, the distance between those two crests right here, that's the wavelength. So this would be an example of a plucked string like a guitar. The wave moves up through the guitar string and then it moves back down. Solids can support both longitudinal and transverse waves. And then the third type of wave is a water wave. Water waves actually move in a circular path. So if that red dot represented a raft in the ocean, if there were no tides pulling you, you would just constantly go in a circle. Now the ocean has a lot going on, so the tides actually move you out from the beach. If you ever got stuck on a raft and got pulled out by the current, that's a little different. The waves themselves create a circular pattern. So you can see here what happens. It's pretty much a combination of transverse and longitudinal. Surface waves don't just happen in water, they also happen during earthquakes. You can have a surface wave through the earth. You may have seen movies or anything where you have a surface wave. You also have a wave underneath the ground, a longitudinal wave with an earthquake, and that's what they use for their seismic readings. They take 3 seismic points and they can locate the epicenter of the earthquake, just like a GPS. But anyway, surface waves move in a circular pattern. What causes waves in solids? An elastic material can create a wave, such as a rubber band. A rubber band, you can put it between your fingers and string it, like in the lab that you're going to do, and that will create a sound. That's an elastic material. A lump of clay does not create a wave. That is an inelastic material. We learned about that earlier when we talked about collisions. Same idea. Elastic is bouncy, inelastic is not bouncy. And then springs also create waves. If you think about a slinky or any kind of spring, you know that you can create waves with that. And this is because there's a force that returns it back to its original shape. Anytime you have a restoring force, you can create a wave. And then waves in air. Longitudinal waves are created in air. It's the only type of wave that you can create in air. And what happens is you compress and you expand the air, which creates these overpressures and underpressures. Kind of like if you have a door that's ajar and you open a window, or if you and then you shut the door. Did you ever notice that the drapes fling out from the wall? because you're creating a low pressure in there, an under pressure, and it causes the drapes to move in that direction. Then when you open the door again, the drapes will push up against the window, and this would be an overpressure. So if you look at the tuning fork here, it's vibrating back and forth very quickly. When it's vibrating to the right or to your right, you'll see that it creates an overpressure, and then when it vibrates to the left, it creates an underpressure. And this vibration back and forth is what creates these areas of compact molecules.